So here's a question. If you have two objects, a wiffle ball and a baseball, being thrown at you, which one of them is going to hurt more if they're thrown at the same speed? I think most of us would probably agree that the baseball is going to hurt a little bit more, but the question is, why does it hurt more? If you asked a lot of people that same question, I think most of them would probably say that it has something to do with the weight of the baseball. But it's more than just weight. So, easiest way to explain this is to think about two objects up in space. Would the wiffle ball or the baseball hurt more if they were in space? Same principle applies to trying to move objects in space. Would it be easier to move the wrench out in space, or would it be easier to move the space shuttle out in space? So if an astronaut had a hand on a wrench and a hand on the space shuttle and pushed off equally with both arms, which object would move the easiest? And the answer is that it's the wrench. Not because it weighs more, because out in space, neither one of them has any weight. The reason why it's easier to move the wrench is because it has less inertia, less mass. So Galileo used the idea of inertia to describe the movement or the lack of movement of objects. You should know that definition for inertia, just that property of a body that resists change in motion. Our learning target number one was to know what inertia is and how mass influences it. So we know what inertia is, now we need to see how mass influences it. Mass is just how we measure inertia, how we quantify inertia. Mass is defined as the quantity of matter in an object. It's the amount of stuff that makes up an object. Depends only on the number and the kind of atoms that make up that object. More atoms, more mass. The bigger the atom, the bigger the mass. We measure mass using a balance, triple beam balance, or an electronic balance. And the units in the metric system for mass are grams or kilograms. Now, don't confuse mass and volume. Mass is not the same thing as volume. Just because something has a very large volume doesn't mean that it has a large mass. The one that I always think of when I think of this concept is the Stay Puft Marshmallow Man from Ghostbusters. Really, really big volume, but not very much mass. Another good example is a giant piece of styrofoam. Very low resistance to change in motion, very easy to move. Very little inertia, so very little mass. Weight is different than mass. Okay, the two are related, but they're not the exact same thing. Weight is just the force of gravity that pulls down on an object. When you're hanging on the monkey bars, it's the force that pulls you downward towards the center of the earth. There's a way to calculate that weight, and this is how mass is related to weight. Part of that equation is mass. So you take mass and you multiply it by a constant called g, the acceleration due to gravity. And here on Earth, g is 9.8 meters per second squared. The units for weight, when you do the math, you're going to end up with a kilogram times a meter per second squared. Kilogram being the unit for mass and meter per second squared being the unit for acceleration. That kilogram times a meter per second squared is known as a Newton. And we abbreviate the word Newton with a capital N. It's a capital because it's named after a person. The way that we measure weight is with a scale. In this case, a spring scale. On Earth, if you do the math and you take the 1 kilogram and you multiply it by g of 9.8, you end up with a weight of 9.8 newtons. And that's about the same as 2.2 pounds. But we don't ever work in pounds in science. We always take kilograms and convert them into newtons. So if you're in pounds, you need to convert to kilograms, and then from kilograms, you can figure out the newtons. So weight is gravity pulling down on a mass, but we know that gravitational attraction varies depending on where you are. If you're on the Earth, you're on the Moon, you're on Saturn, you're going to get a different value for G. Here on Earth, G has a value of 9.8. If you go to a smaller planet like Mars, Mars has a G value of 3.7. So you're going to actually have less weight on a smaller planet. Smaller planets have less gravity, so you end up with a smaller weight. Bigger planets like Saturn, which has a G value of 11.2 meters per second squared, is going to give you a bigger weight. So the larger the planet, more gravity, the bigger the weight. And those are the last two learning targets. Learning target number 5 is to know that weight is a force that depends on acceleration due to gravity, which varies from planet to planet. Learning target number 6, that you can define the Newton as a unit of weight.